Welcome, everyone. Today, we're diving deep into the secret behind token efficiency in LLMs.
You know that feeling when you type a question into an AI and boom, you get a perfect answer in seconds? It totally feels like magic, right? But it's not. It's actually a really clever process that all starts with one single, absolutely crucial step: turning our words into numbers. If the AI gets that first step wrong, well, the magic just fizzles out. So let's break down exactly how it all works. Okay, so here's the fundamental problem we're up against. On one hand, you've got human language, messy, full of nuance. And on the other, you've got a machine that only understands numbers, literally just ones and zeros. So how do you bridge that massive gap? How does an AI read this very sentence that you're looking at right now? Well, the answer is a fascinating process called tokenization. Right, so tokenization, that's the name of the game. It's the essential first step. You can think of it as the AI's way of reading. It takes our text, breaks it down into smaller, manageable chunks called tokens, and then, and this is the key part, it converts those tokens into numbers that the model can finally process. And how you decide to chop up that text, well, that choice has a huge ripple effect on the model's performance, its memory usage, and just how efficient it is. So, at its core, you can think of tokenization as building a custom dictionary for the AI, a vocabulary, right? But the big question is, how do you decide which words, or even parts of words, get to be in that dictionary? Turns out, there are two main philosophies for how to chop up our language. All right, first up, we've got something called byte pair encoding, or BPE for short. The strategy here is actually pretty simple, but it is incredibly powerful. It starts with the absolute basics, a list of every single individual character. Then it dives into a massive pile of text and starts looking for the most common pair of characters. When it finds one, it smushes them together to create a brand new token. Okay, theory is great, but let's make this real with a quick example. Imagine all the text we have is just the phrase low, lower, lowest. So BPE starts with the most basic building blocks, the individual characters, LOWERST. It scans the phrase and sees that the pair LO shows up a lot. So merge. It creates a new token, low. Okay, now it scans again. What's the most common pair now? It's low. So merge again. And this just keeps happening over and over. Find the most common pair, merge it, repeat, until the dictionary hits its predefined size. And this right here, this is the real beauty of BPE. Because it builds its dictionary from the ground up, from individual characters, it's fantastic at handling rare words or even brand new words it's never encountered before. So instead of seeing a new word and just throwing up its hands like, I don't know this, it can simply break it down into smaller, familiar subword pieces that it does know. It's super flexible. So this really gets to the heart of the two competing philosophies. You have BPE, which is all about raw frequency. It's constantly asking, what's the most common character combination I can find and merge? It's a numbers game. But then you have the second method, WordPiece, which asks a totally different, kind of smarter question. It asks which combination, if I merge it, will make the overall sentence more predictable for the model. It's a subtle shift, but it's a really crucial difference in strategy. So let's dig into that second method, WordPiece. This is the algorithm that models like BERT use. Instead of just counting what's most common, WordPiece is all about maximizing likelihood. What does that mean? Well, it basically trains a little language model on the side. And with every possible merge, it asks itself, which of these choices is going to make the training data look the most probable, the most predictable? It's trying to create a dictionary that gives the model the best possible clues for what comes next. This often results in a vocabulary that's more meaningful, semantically speaking. And you can see this in action in some of the biggest models out there. You take Google's super influential BERT model, for instance. It uses this exact WordPiece algorithm to build its dictionary. And its vocabulary size, a very specific 30,000 unique tokens. That number wasn't just picked out of a hat. It's the result of a very careful balancing act between different design priorities. And that brings us to the great vocabulary trade-off. This is a huge deal. When you're designing a large language model, you are constantly in this tug of war between processing speed on one side and memory usage on the other. And the size of your vocabulary, that dictionary we've been talking about, is right at the center of this battle. It's critical because it directly impacts how much it costs to run these things and how fast you get your answers back. Just take a look at these numbers on the charts. If you go with a smaller vocabulary, let's say around 32,000 tokens, your sentences get chopped up into more pieces. This means your text sequences are about 15% longer, and that slows down processing.
But, and this is a big but, the upside is massive. You can slash the model's memory footprint by up to 40%. On the flip side, a big vocabulary gets you faster processing because the sequences are shorter, but man, it is a total memory hog. And this isn't just some theoretical problem you'd find in a textbook. This exact trade-off, speed versus memory, is what dictates how the biggest, baddest, state-of-the-art models are actually designed in the real world. The choice of which tokenizer to use and how big to make the vocabulary, it tells you everything about the core priorities of the people who built the model. This table really lays it all out, a kind of model showdown. In one corner, you've got BERT. It uses WordPiece and a relatively small 30,000 token vocabulary. Its goal? Optimize for a smaller memory footprint and maybe faster pre-training. But in the other corner, you have GPT-4. It goes a completely different route, using BPE with a massive vocabulary of over 100,000 tokens. Its priority is clearly on creating shorter sequences, which helps it understand really complex, nuanced ideas, even if that means using a whole lot more memory to do it. Okay, so let's boil this all down. What are the key takeaways here? First, tokenization is just how an AI learns to read. It's all about turning our words into numbers it can work with. Second, the two main recipes for this, BPE and WordPiece, are all about merging chunks of text based on either how frequent they are or how much they help predict what's coming next. And finally, the whole thing is one big balancing act. The core challenge is always this trade-off. A larger vocabulary gives you faster processing, but it's going to cost you a ton in memory. And that leaves us with one big question to think about. As these AI models keep getting more and more powerful, do you think we'll ever discover some kind of perfect vocabulary? One that gives us the best of both worlds? Or is this fundamental tension, this trade-off between speed and memory, something that's just always going to be part of the game?
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.